All right, the last thing we are looking at is how to model with a linear function. So recall that when a real world situation involves a constant rate of change, a linear function is reasonable model for the situation. The situation may require restricting the function's domain. So looking at this example here, we are told to write a function that models the given situation, determine the domain from the situation, and graph the function using the domain and identifying the range. So example A says Joyce jogs at a rate of 1 mile every 10 minutes for a total of 40 minutes. Use inequalities for the domain and range. Okay, so step one is to identify and define the independent and dependent variables. When we look at this problem, you have to think, does the distance she run depend on the time she runs for, or does the time she runs for depend on the distance she jogs for? In this case, our independent variable would be the time in minutes, and we're going to label that as t. Our dependent variable would be distance in miles, and we are going to label that d. Okay, so the distance she runs depends on the time she runs for, right? She can run for 20 minutes and maybe get in 2 miles. Not she's going to run for 2 miles and get it in for 20 minutes. So there is a big difference in how we define that. Okay, second step is to find the rate of change. And remember, the rate of change is found by the change, and we use delta, this little triangle is delta, change in dependent over the change in our independent variable. In other words, y over x. Okay, so we already said the distance depends on time. So what is the change in distance? It tells us that the rate of change is 1 mile every 10 minutes. It's already set up for us. So 1 mile over 10 minutes. Okay, now this does give us our slope or rate of change. So in this case, it is 1 over 10 miles per minute. Okay. Step three, find the y-intercept. Now, the y-intercept, when we're thinking about distance, if we're measuring how far we're running, where do we start? Think about it. Do we start at half a mile already run? Do we start at a mile already ran? No, we start at 0, right? From the time we start running to the time we stop, that is the distance we measure, so we start at 0. Step four, write the function and identify the domain. All right, our function, how do we put this into a function? We're going to use slope-intercept, okay? We're measuring distance according to time, so d's of t. Our slope, or our rate of change, is 1 over 10, depending on how much time she runs for, so t, 1/10 times t. And then our y-intercept is 0. You can put plus 0, it's not needed, okay? And now let's define the domain. So for the domain, and we were told to write it as an inequality, our domain x values, right, our time, well, we're going to define that as 0 for time up to and including our endpoint. How much time does it take? How much time is she running for? Well, it tells us right here she's running for a total of 40 minutes. So from 0 to 40, that is our domain. Step 5, graph the function and identify the range. All right, so let's go ahead and graph the function. Now, we know we're starting at 0, 0, right? Time is 0 and distance is 0. So I'm going to label my axis, distance in miles, and time in minutes. Okay, and let's just go by tens. Actually, let's go by fives. So she runs 5 minutes, 10 minutes, 15 minutes, 20, 25, 30, 35, 40, 45 minutes. And I'm only going up to 40 so I can stop there, okay? All right, now our y-axis, distance in miles, we're going to label this, Let's go by half a mile. So 0.5, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. And I'm going to stop there. Okay. Now let's figure out how much she runs in those 40 minutes. We're going to substitute 40 for time. 1/10 of 40 is 4. So in 40 minutes, she runs 4 miles. And we can actually write this as a coordinate point, 40, 4. Go over to our table, 40 minutes, right? This is the mark, our 40-minute mark. And 4 miles is this segment here. So we can see we need a point at 44. Connect our points. Draw as straight a line as you can. And there is our function. This shows us how much she runs according to time. Now, our range, as in inequality, goes from 0, d's of t, that's our y value, up to 4, right? The domain, she runs for 40 minutes, from 0 to 40 minutes. The distance, she runs from 0 to 4 miles. Okay, looking at B, B says a candle 6 inches high burns at a rate of 1 inch every 2 hours for 5 hours. Use interval notation for domain and range. All right, so let's follow the steps in the previous example. First step is to identify your independent and dependent variables. In this case, you have to determine, does the height of the candle depend on the time it burns for, or does the time it burns for depend on the height of the candle? If you said that our independent variable is time in hours, you are correct. Let's go ahead and use t, or you can use x and y, variables don't matter. Our dependent variable in this case would be the height of the candle, height of the candle in inches. Let's use h for height, okay? Or height according to time, h of t, however you want to label it. Second step is to identify your rate of change. Now, we were told what our rate of change is. It tells us it burns 1 inch every 2 hours. Remember, it is dependent over independent. So height, 1 inch, over time, 2 hours. Okay. Now, in this case, you have to think about, is it a positive slope or a negative slope? We're burning the candle. It's losing height. So in this case, we would have to make our slope or rate of change a negative 1/2. It is losing height. Okay. Our third step was to find the y-intercept. Well, our y-intercept is where we start, and we're measuring a candle that is 6 inches high. So in this case, our y-intercept would be the 6 inches, the height of the candle. Okay. Step 4, write your function and identify the domain. So height, h of t, is equal to the slope according to the time it burns plus 6. Okay, our y-intercept is positive, plus 6, we are starting at 6. Now, the domain. Our domain is our independent variable, time in hours. So how long will the candle burn for, right? Where do we even begin? Do we start counting before we light the candle or after we light the candle? We start counting when we light the candle. So we start at 0, and how long is the candle going to burn for? In this situation, you are told that it burns for 5 hours, right? So our domain goes from 0 to 5. Now the question is, do we include the points or do we not include the points? We do include them, right? Because it starts when we light it, it ends when we extinguish the flame. So 5 is included because that's when we are cutting off the flame. Step 5 is to graph the function and identify the range. Okay. Now, we do have our starting point which would be 0, 6, right? It starts at time 0, a height of 6 inches. Where does it end? It ends at 5 hours, so this is when we would go in and substitute in for the function. So 5, negative 1/2 times 5 plus 6. Negative 1/2 times 5 is negative 2.5 plus 6 gives us an ending value of 3.5. So at 5 hours, we are at a height of 3.5 inches. Okay, going to graph this, remember to label your axes always. Time we are measuring in hours, so I'm going to go by ones. And height is measured in inches, and again, I'm going to go by ones. So up to, we know the candle is 6 inches. I'm going to go all the way up to 7. Now we already have our points. We can just graph those. We know that they are included. So for 0, 6, and then 5, 3.5 is the new height of the candle. Connect your points, and you have your function. Okay, this shows us, it gives us a model, a linear model of what the candle will look like after burning for several hours. Okay. All right, now go ahead and hit the pause button and try C. Come back when you have your answer and your graph. All right, this is what you should have for C. First of all, you should have identified that our independent variable is time and our dependent variable is distance, right? We are moved forward 25 feet every 15 seconds. So rate of change, 25 over 15 can be reduced down to 5/3. Okay, so it's 5 over 3 feet per second. Y-intercept, start at 0, right? We can't move if we're not on the moving walkway, so we're starting at 0 when we get on. Our function, d's of t is equal to 5/3 t. Domain would be 0 up to 60 seconds. Okay, I know it asked you for 1 minute, but remember we are measuring in seconds because our rate of change is per second. So 1 minute is 60 seconds. Starting point, 0, 0. We don't move if we're not on the moving walkway. Finding our ending point at 60 seconds, we are at 100 feet. So our range, 0 to 100. Draw your points, starting at 0, 0, ending at 60 seconds at 100 feet.